Welcome to the lesson on section 10.1, Modeling with Differential Equations. In this lesson, you'll learn how to show that a given equation is a solution to a given differential equation, and how to solve an initial value problem involving a differential equation. A differential equation is basically an equation that has one or more derivatives in it. xy prime plus y equals 2x is an example of a first-order differential equation because y prime is the highest order derivative in it. Y double prime plus 2y prime minus 6y equals 0 is an example of a second-order differential equation because a second derivative is the highest order derivative in it. As a first example, I'll show that y equals e to the negative 2x is a solution of the differential equation y prime plus 2y equals 0. The derivative of y is negative 2 times e to the negative 2x. Substituting that for y prime and e to the negative 2x for y in the equation, I can see that negative 2 e to the negative 2x plus 2 e to the negative 2x equals 0. When you're asked to show something, be sure to make the conclusion fairly obvious. This one didn't require any additional steps to make it more obvious that both sides of the equation were equal, but you may need to show more steps in other examples. Example 2 has two parts. First, I'll verify that the equation y equals the constant times x to the third solves the given differential equation. Then I'll find a solution that passes through a particular point. So to verify that y equals cx to the third is a solution, first find its derivative, 3cx squared. Then substitute for y prime and for y in the differential equation and show that the two sides of the resulting equation are equal. Continuing to part B of this example, the solution we seek is called a particular solution because y equals cx to the third is a family of curves that would satisfy the differential equation. We'll find a solution that passes through a particular point. Because we're given a particular point through which our solution should pass, this is called an initial value problem. Substitute the values of x and y into the equation y equals cx to the third and solve for the constant c. This makes our particular solution y equals negative 2/27 x to the third. In this example, I'll explain why the graphs below cannot represent particular solutions of the differential equation dy dt equals t squared times y minus y cubed to the fourth. This problem will serve as a helpful lead-in to the return of slope fields in our next lesson. The first thing I would look at is the values of t or y at which the slope of the graph dy dt should be 0. I can see from the differential equation that dy dt equals 0 when t equals 0, or when y is 0, 1, or negative 1. So the first graph, drawn in blue, can't be a solution to this differential equation because it doesn't have a slope of 0 when y is 1. The second graph in green can't be a solution to the differential equation because it doesn't have a slope of 0 when y is 0. And the third graph can't be a solution because the slope isn't 0 when t is 0. If these didn't help, then something else we could also have looked at is when the slope should be positive or when it's negative. If you look back at our differential equation, you can see that no matter what the values of y and t are, the slopes will come out to be positive numbers. So we have a few examples here, specifically the blue one and the orange one, that don't have positive slopes everywhere, so that would be another reason why they couldn't solve this differential equation. This concludes the lesson on section 10.1, Modeling with Differential Equations.